Hi everyone, this is Unit 1.8, inverse functions. Inverse functions are one of the biggest ideas that we've talked about in math to this point. We've used it in basically ever since Algebra 1, but really we've understood inverses going way back to the beginning. Understandings specifically that inverses undo one another, thinking about like addition and subtraction or multiplication and division. I think that's the type of inverse we've seen in the past, right? That they undo one another. But more specifically, we're going to get into a little more detail as far as what's really going on with inverses. One of the big takeaways will be that we will literally switch the role of our input and our output, in this case x and y, and we'll see how these graphs and their related functions interact with each other. So some notation, when we talk about inverses, we will call this the inverse of f of x, but we write it almost like a -1 exponent. We would read this as the inverse of f of x. So when we see that -1, you're not creating a fraction, you're not creating a denominator, you are creating an inverse. So let's use an inverse here. So we have the function x minus 1 all divided by 3. This is a linear function. I'm just going to manipulate it into a form we may recognize a little bit better. I'm just going to basically apply that dividing by 3. So I'm going to rewrite this as f of x equals 1/3 x minus 1/3. And if we want to, we can even graph that. It's a little tricky to do so. It's a linear function, and we know 2 points, so let's just build off of that. We know that the point 1, 0 and the point 4, 1 are on our line, and if I know 2 points on a line, that's enough. So I can draw the line through those 2 points, and that's what our function looks like. We will come back to this graph in just a minute. But here we need to get some steps. So we're going to find the inverse of this function. The way we're going to do this, it's going to be in 3 steps. The first step, we are going to rewrite as a y equals statement. So we can rewrite this as y equals 1/3 x minus 1/3. Our next step, we flip x and y, and we're gonna, an inverse is defined by the reversal of the roles of input and output. We're gonna do that literally with the second step. We're gonna flip x and y, so x will equal 1/3 y minus 1/3. And our final step is going to be solving for y. So I'm going to clear my fractions. You can see that everything is in thirds, so 3x equals y minus 1. So we can solve this for y as 3x plus 1. I just barely got enough space there. So let's take a look at that graph, this y equals 3x plus 1. Well, that's in slope-intercept form. We know that it has a y-intercept of 0, 1. And this line has a slope of 3. And if we were to connect those 2 points, we would see the graph of our inverse. And I'm just going to do one more thing just so we can see it. We're going to label those points. We have 1, 0, 4, 1, and then we also have 0, 1, and 1, 4. So this is what happens when we graph an inverse function. We can see that x's and y's switch roles. We'll also notice that this graph has symmetry. It's not perfect just based on how I drew it, but if it were, it would go, and these 2 graphs would be symmetric about the line y equals x. They are mirror images on either side of that line. So if the original contained 1, 0, and 4, 1, the inverse contains 0, 1, and 1, 4. We've now drawn both of these in, and we can see it's a reflection over the line y equals x. So that first page, this is the idea of an inverse. Inverse changes the role of x and y, changes the role of input and output. When we graph inverses in the original function, they are reflected about the line y equals x. So let's look at it a little bit more formally. The graph of an inverse of, in this case of f, is found by literally flipping x and y coordinates. It makes sense if we do it algebraically, we switch x and y, that if we also did it graphically, we would also just have to switch x coordinates become y coordinates and y coordinates become x coordinates. F and g are inverses if, and here we're going to pull in some work we did in our previous class, f of g of x equals x, and this is a two-way street. We need to check both. G of f of x also equals x. So if I want to check for if functions are inverses, I need to perform both of these tests. I need to compose these functions. I need to take f of x and compose it into g of x and g of x into f of x. What I want to see is that those two functions undo one another, and we get back to our starting point, which will be x. So we're going to look at some examples. I'd like you to try these on your own first. You can see here there's one sketch. We're determining inverses and whether or not functions are inverses. So what I'd like you to do is try these problems. Obviously, not much time will elapse once we unpause this, but I want you to try to go ahead and graph this function, thinking about what we can do with x and y coordinates. All right, checking with you guys in a few. All right, with some movie magic, let's check in on those problems. So when we see a problem where we're trying to sketch a graph, the big idea with inverses is we need to flip the role of inverse and outverse, flip the role of x and y. So we can do that literally with the points. Each point on the original graph has a corresponding point on the inverse. So I'm just going to highlight those so you see them. And you can kind of compare my work against yours. I also sketched in that line y equals x. That's a highlighter. I probably shouldn't write with that. I sketched in this y equals x here just to visualize. Some of these graphs do seem a little strange, and they can be a little counterintuitive to reflect, but it can be useful at the end to just make sure you got to the right place. Let's check to see whether two functions are inverse. So on 2a here, they give us two functions, and as we look at them, we can kind of make sense of the operations here. We can see one is multiplying by 4 and then subtracting 7, the other, adding 7 and then dividing by 4. Well, what we need to do is compose our functions. In both cases, in both black and in blue here, when I compose f into g or g into f, the result is x. In order to prove that these functions are inverses, I must show both. Now, if I move over to example B, I can perform the same operation, right? Trying to test for inverses. And what I find is that by picking one of them, I can see that the result is not x. I would say that's enough for us to say, pause. We didn't get the answer we wanted. One of these is enough to disprove inverses, But if we want to prove inverses, we need both. In this case, because we got no as an answer, we don't need to reinvent the wheel. Let's find some inverses. We're going to follow that same process from page 1. We're going to flip x and y. We're going to, rewrite it as a y equals, flip x and y, and solve for y. All the while, I'm using inverse operations to solve, and my result is the cubed root of the quantity x minus 1. On number 2, we have a little bit trickier function. This is a rational function with that denominator with the variable in it. The solving's a little trickier. Maybe somebody had some difficulties going from here. I'm realizing I kind of skipped a step. So what I really did here is I multiplied both sides by y. Right, so I cleared that y off the right-hand side of my equation, then divided both by x plus 3. Just to make sure you guys saw that move. So we have our inverse. You can see there, the inverse of g of x is 2 over x plus 3. Example 3 is a little bit tricky. We follow the same first few steps, and I bet about 99% of us got to here. And I think a few of us may have missed this plus or minus. So it may be helpful to think about the graph of a quadratic, right? I can think of that U-shaped parabola. Its inverse would just be turned on its side, right? The inverse would end up being turned on its side, something like that. But we don't really graph square root functions like that, so we need to include both the positive and negative. We'll talk more about that in a minute. Finally here, we're going to talk about horizontal line test, one-to-one functions, and domain restrictions. So what we noticed in that last third example was that writing an inverse kind of got tricky with a square root, right? There was points on that inverse that, negative 2, 5, and 2, 5. How do I switch x and y if not every y has only one x companion? So we're going to just talk about a few more vocab terms, okay? First thing is the horizontal line test. It determines if the inverse of a function is also a function. If those conditions are met, this means the function is one-to-one. A one-to-one function passes the vertical and horizontal line test. The vertical line test tells us it's a function. The horizontal line test tells us that the inverse is also a function, making that function one-to-one. Now, we like dealing with functions. Whether we're dealing with inverses, original functions, whatever. So in cases like 3C, we usually introduce domain restrictions. Basically, we restrict the domain of the original function to guarantee that the inverse is also a function. Basically, we cut half of the quadratic parabola off, so when we flip it on its side, it's a square root function. So what we do is find the inverse of h of x, and we'll use that set builder notation such that, so we want all values x such that x is greater than or equal to 0. By restricting the domain of the original function, we now guarantee functionality of the inverse, and it just opens up some opportunities for us, mathematically speaking. That's where we're going to pause for today. Thanks, everybody.